it. All right, so starting again for the first time, convolution. Convolution is this thing that fixes, so the Laplace transform product is not the product of the Laplace transforms, but this thing called convolution satisfies that. So let me give you the definition here. Well, I lost it already. So the convolution of f and g is the integral from 0 to t f of t minus v g of v dv. That is not what I wrote in the break. But, well, it turns out, let me just tell you, it turns out after we work a little bit more that this is also equal to g convoluted with f as it happens. So like the convolution product is commutative. I don't think that's immediately obvious from the definition, but it's true. So what you may remember from a dream or from some deleted lecture is I wrote the g and the f reversed. It doesn't matter. It's the same thing. All right, so I'm going to work through the proof on page 400 because apparently I need to. Here we go. The Laplace transform of the convolution is the integral from 0 to infinity, e to the minus st. The integral from 0 to t, f of t minus v, g of v dv. Now, he says this. He says, to simplify the evaluation of this iterated integral, we introduce the step function, u of t minus v, and rewrite the inside integral as an infinite integral as well. So maybe you guys can tell me. I just, there was something about this step that I was having trouble parsing. Does it make sense to you guys? Finish writing it down, and then you can decide whether you think it makes sense or not. Does that make sense? I mean, I'm assuming he's adding 0 by doing that in a kind of sneaky way, right? Oh, that does make sense. If v is bigger than t, what happens? What's t minus v if v is bigger than t? It's negative, right? So the unit step function is 0. So this unit step function, this is 1 for 0 less than or equal to v less than or equal to t, and it's 0 otherwise. So that's just equal. Okay, fine. Now I'm on board. I'm on board. I had some mental block to that when I was trying to write it out just a second ago. All right. Anyway. Now, he says, okay, so reversing the order of integration, reversing the order of integration gives the following. The integral from 0 to infinity, g of v, the integral from 0 to infinity of e to the minus st, u of t minus v, f of t minus v, dt, dv. I think I can buy that, right? There's no t dependence on the g of v, so we can factor it out, right? Make sense? Yeah. Then what? He says, recall from the translation property in section 7.6 that the integral in brackets equals, oh, very sneaky. Oh man, the proof I've seen of this before was rather different. This is much better. I guess I shouldn't be surprised. I'm kind of annoyed at myself that I haven't looked at this proof, given that I'm using this book. I mean, I must have looked at it at some point. But anyway, so this is what? What is this? that's one of the things we've been using today, right? I mean, what happens, what was the, remember? So like inverse Laplace transform of e to the minus as f of s was what? Let me use an h here. That was the theorem we worked out last time was that was h of t minus a times u of t minus a, right? In other words, but you know, by the same token, the Laplace transform of h of t minus a times u of t minus a, right, is e to the minus as h of s, right? Now here, if you look at this, what is this? This is the Laplace transform, right? This is the Laplace transform of f of t minus v, u of t minus v, right? So by the theorem that we've been using and we derived yesterday, last week, we have the integral from 0 to infinity of g of v, what is it? E to the what? E to the minus, now what's playing the role of a here though? V. V is like the a, right? So it's e to the minus vs, and then f of s, right? Sorry. I'll get it eventually. But f of s has no v dependence, right? So we can pull that out of the integration. And what's left? Sorry it's taking me so long to get through this, you guys. It's my fault. Every so often I get stuck on something. This is, for me, the thing in this course I get stuck on. But what's left with is that's the Laplace transform of g, right? Integration over v from 0 to infinity. So there you go, f of s, g of s. And that's the theorem. This is the convolution theorem, that the Laplace transform of the convolution is the product of the transforms. This is really a very beautiful, beautiful formula. So how to use the transform? What example am I on? It's been 6. All right. I got to pick up the pace here. It's here. Example 6. So here, let me show you sort of an elementary use of the convolution. If we have y prime prime plus, let's say, 3y prime plus 2y equal to g, all right? And I guess keeping with the theme of today so far, y of 0 is y prime of 0 is 0. I'll eventually make that non-zero, just maybe not today. We saw what happens when that's non-zero yesterday, right? I mean, so, yeah. Take the Laplace transform both sides. What do you get? You get s squared, big Y, plus 3sy plus 2 big Y equals big G, right? In other words, solving for y, we get y is equal to 1 over s squared plus 3s plus 2, right, times big G. So if I know about convolution, I can say, aha, so y of t is equal to the inverse transform of this thing convoluted with the inverse transform of big G at time t. Yeah, so like, by the way, we could say this, the inverse transform of big F times big G is the, well, I say this, it's the inverse Laplace transform of F convoluted with the inverse Laplace transform of G. Don't get lost in the curly brackets here. I'm just changing the notation. I mean, of course, you could also say that this is F and this is G in our usual notation. But if you don't know what F and little g are, then maybe it's a nice in-between step to have. Okay, so it's the convolution of the inverse transforms of those, right? Now, my example 6. We actually already know that the inverse Laplace transform of big G is what? That's just what we called little g. You notice I didn't actually tell you what it was. Right? What's the inverse transform of this thing? I need to do a little calculation. Not too much, though. This is s squared plus 3s plus 2. That should be something like a over s plus 1, right? Plus b over s plus 2. What's my a and b? Can you guys tell me? Can you work that out? Learn my lesson. Stir it before I get to the end. So you got algebra, a equals 1, b equals minus 1. Very good. So y of t is going to be, well, let me just do that here. What's the inverse transform then? 1 over s squared plus 3s plus 2. That's the inverse transform of 1 over s plus 1 minus 1 over s plus 2. We can do that, right? That's e to the minus t minus e to the minus 2t, right? And thus y of t should be the convolution of e to the minus t minus e to the minus 2t convoluted with g, right? Now that is actually the integral from 0 to t of e to the minus parentheses t minus v. Well, guys, we should be smart about this. Do you want to put, it's whatever. Let me stop trying to be smart and just write what's obvious here. So we replace t with t minus v. We take that, we multiply by g of v dv. That's the convolution. Let's see here. me rewrite this somewhat suggestively. You tell me what we got. This is also e to the minus t, the integral from 0 to t of e to the v g of v dv minus e to the minus 2t, the integral of e to the 2v g of v dv. I mean, sorry, I'm burying the lead here. So just stick a fork in it. You know, it's done here, right here. That's the answer, okay? Now, what I'm doing at the moment is I'm trying to connect it to other things we've already done. We had a method to find integral solutions to second-order differential equations with sort of arbitrary forcing functions before. What was that method we used? Remember? Variation of parameters, right? Variation of parameters was another method that would allowed us to solve this problem before. So I'm trying to see here is, can I see the variation of parameters formulas? What would a variation of parameters look like here? We have to pick our y1 and y2. What would y1 be? What would y2 be? You know, it's lambda squared plus 3 lambda plus 2 equal to 0. So I have lambda plus 1 times lambda plus 2. So I suggest that y1 would be e to the minus t, and y2 would be e to the minus 2t, right? What's the Wronskian? So when we calculate like v1, the integral of, what is it? It's y2 minus y2g over the Wronskian, right? That would be the integral of minus e to the minus 2t g over minus e to the minus 3t dt, right? AKA the integral of e to the 2t g dt. But we did the integration in terms of the dummy variable v and integrate to t, right? But you can see that that's exactly what we had here. I'm sorry, I can't do math. What's 3 minus 2 is 1. Yeah. Okay, so that is straight up the variation of parameters formula. Okay? But I think logically, once you're familiar with Laplace transforms and inverse Laplace transforms, convolution gets you to this integral formula much faster than variation of parameters. And also, this convolution idea, finding the solution for an arbitrary forcing function, it's just as easy to do for a third order or fourth order problem using convolution. Like I could not in good conscience ask you a variation of parameters third order problem. But with convolution, you could find the arbitrary solution to an arbitrary inhomogeneous problem for a third order problem without even breaking a sweat. Like here, let's do it. Example 7. Suppose we had, I'll keep it relatively simple, y prime 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 plus y prime equal to g. And I'm feeling guilty for not including any initial conditions. So this time I'll say y of 0 is 1 and y prime of 0, 0, y prime prime of 0, 0. Let's find an integral solution to this using convolution. So we get s cubed y. And then what am I supposed to do? So what's next? What's the derivative theorem say I should subtract from that? Minus something, you guys tell me. Plus s times big Y. I'll do the easy part, minus 1. Equals to big G, yeah. So what goes there? Fill in the blank for me. There's an s squared. I know that. Well, I'm not. I think it's s squared. Yeah. So just we subtract s squared because the general rule, of course, is the Laplace transform of y prime 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 is equal to s cubed big Y minus s squared y of 0 minus s y prime of 0 minus y prime prime of 0. That's the rule for the third derivative. We haven't seen it in examples yet, but that is what it is. Okay, so then this gives us what? This gives us s cubed minus s times big Y equal to s squared plus 1 plus g. Yeah? Ah, cool. This was not intended. I mean, this is an accident. I just made this problem up, but something really, really neat happens in the next step. So y is equal to s squared plus 1 over s squared. Hey. Oh, yeah, sorry. It is still very neat. I've made a mistake here. What is my mistake? I mean, yes, yes. That really matters because when I factor, this is s squared plus 1 times s, right? And then plus 1 over, s squared plus 1 times s times g. All right. I was kind of giddy because, at least the term due to the initial conditions, at least those I don't have to do any partial fractions for, thankfully. That's just 1 over s. Hooray! I mean, that's nice that that happened. Okay? On the other hand, this piece, I should probably do partial fractions for that before I go on here. All right, so what's the partial fractions for this? We want 1 over s squared plus 1 times s equal to a over s plus bs plus c over s squared plus 1. Let's work that out. So 1 equals to a times s squared plus 1 plus bs plus c times s. I'll put s equals to 0. That gives me a nice equation. 1 equals to a. Yeah, that's kind of nice. If I put... Oh, well, I guess I'll just usually past this point. It helps to do the algebra. This is s squared times a plus b plus s times c plus a. So the constant term gives me 0 is equal to c. I mean, not the constant term, but the term with s, coefficient of s. It's like, and then s squared, I get 0 equals to a plus b. Equating coefficients. So it looks like c is 0 and a is 1, b is what? B is minus 1, right? See, now we're good to go. We can calculate y of t is the inverse transform, right? Take the inverse transform of big Y. Now the 1 over s, that just gives me 1. Which I suppose isn't surprising in retrospect, because my initial conditions are like y of 0 is 1, and the second and the third, first and second derivative are 0. It's like 1 does that for me. That kind of makes sense to me. And then this plus the convolution, right? Let's see here. So we're going to convolute 1 minus, what is this? Cosine t, right? Inverse transforms to cosine t. So I should take that and convolute it with g. So my solution, integral solution, is 1 plus the integral from 0 to t of 1 minus the cosine of t minus v times g of v dv. There you go. That's the integral solution to this problem. Any questions? All right, so I owe you guys a short discussion about the transfer function, so let me do that. If you look at what we've been doing, you can ask yourself, let me just kind of sketch what we're doing in general, all right? So here's the generic setup of what we're doing. We've got some differential operator, right, L. Well, more specifically, we've got some polynomial in the differentiation operator, right? This thing acts on little y, and it gives me g of t, right? And if we have that y of 0 is y prime of 0, and so forth and so on down the line, it's really, really easy to explain what happens when we take the Laplace transform, right? We've seen this again and again and again in all of our examples. So this is example 8, which is really more of a meta example. It's an example of examples, right? In fact, it's more of a comment than it is an example, honestly. But if these are all zeros and we take the Laplace transform, what do we get? We just get the polynomial, instead of being in terms of derivatives, it just ends up being in terms of s, right? Like we started with, if you want to, this was really d cubed plus d times y, acting on y equals to g, right? But what happens? We took the Laplace transform, and it changes the d's to s's, right? So really, if you look at the pattern, what we have is the polynomial of s multiplied in the s domain by big Y equals to the Laplace transform of little g, which we call big G, right? And so then we do y is equal to 1 over the characteristic polynomial in terms of s times g, and therefore little y of t is equal to the inverse transform of 1 over p of s convoluted with g, and that's our solution. So, a little bit of name calling here. In engineering, and also in the textbook at some point, I think you look in the index, you'll find it. This 1 over p of s is sometimes denoted h of s, 1 over p of s. This is the transfer function. Transfer function. So what if we just have y, what if we end up with y equals to 1 over p of s? What would that mean about g? If we go through this process and we find that y equals 1 over p of s, what would that say about big G? It would say that big G was what? I mean, just, you can look at it. G would be 1, right? What would that say? What's little g then? If big G is 1, what's little g? Started today. We talked about the direct delta function, right? The Laplace transform of the direct delta function is 1. So this would be delta of t. So if you find the solution corresponding to the inverse transform of the transfer function, that corresponds to solving the system subject to the unit impulse force, right? So this y equal to h of t is the solution to P of d dt acting on y equal to delta function of t, where again all the initial data is 0. So my generic solution is really, again, to write it in terms of my notation, if we call this thing, I mean, we call 1 over, this is h, right? The inverse transform of the transfer function. So this is h convoluted with g of t, or if you like, that's the integral from 0 to t. Let's see here. H of t minus v, g of v dv. Or you could write this, the integral from 0 to t, g of t minus v, h of v dv. I mean, whatever you like. And if you think about that, you can think about constructing the whole solution from the responses to a bunch of different unit impulse functions weighted by some scalar factor. There's a principle of superposition you can look at with this integral and see how you're building the general solution from these like fundamental unit impulse solutions. Anyway, you continue on this story and you'll learn about these things called Green's functions, and that's a deeper topic that I don't have time to really get into deeply here, but I just wanted to make a comment about it. And also because this just sort of ties together a bunch of examples we just did, right? Which are, good test questions or whatever, because these are nice test questions, aren't they? Because they involve everything we've been doing, and they kind of tie things together. You don't actually have to do the integral at the end, right? That's nice. But you can see, if g of v is a direct delta function, then all of a sudden the integral becomes easy to do also, by the way, right? If this was delta of v, then you just, plug in v equal to 0, and you get 1 minus cosine of t from that, All right, enough about that. So that's almost everything I have to say about Laplace transforms. One final comment about Laplace transforms, then I'll go on to series with our remaining 20 minutes. The other comment I have is sometimes Laplace transforms pay off big for sequences. So, good grief. Let's try that again. So here's one of my favorite systems of differential equations. Try to solve, x prime equal to minus y, and y prime equal to x. We've solved this before. If you use the eigenvector technique, it's going to be a complex eigenvector problem. This is really nice to solve. We're going to assume x of 0 is 1 and y of 0 is 2, just for the sake of discussion. I want to show you how we can solve this using Laplace transforms. So Laplace transforms can also be used to solve systems of differential equations. The words I was looking for a minute ago and couldn't find. So take the Laplace transform. We get s big X minus 1 equals to minus big Y. this gives us s times big Y minus 2 equals to big X. Wasn't bad, was it? And now we have two equations and two unknowns. So we just have to solve for big X and for big Y. But it's two equations and two unknowns. So you got to do some, basic linear algebra. I kind of like this one, right? Like it's easy to solve for X there. So maybe we can take that and substitute in the first one. So that's S times S big Y minus 2 equals to minus 1 equals to minus Y. So we get S squared plus 1 times big Y equals to 2S plus 1, right? And so Y, big Y, is 2S plus 1 over S squared plus 1. And yeah, so I can take the inverse transform of that, and that gives me the solution for Y, right? Y of t is 2 cosine t plus the sine of t. Now, if you're a slave to the method, you could go back and plug in what we learned for big Y into the formula for big S, right? Big X, and then take the inverse transform of that. But I think that's a dumb way to finish this problem. What's the smart way to find the rest of the solution? You can tell me, Nathan. That's a non-degenerate comment today, so there's no doubt which Nathan I mean.
Plug it into Y.
Plug it into Y.
And X prime is good minus Y.
That would be one thing you could do, but be lazier. Be lazier. Look at the second equation. Right. See, like X is the derivative of Y. So embrace the differential equation. And there you go. And I'm quite certain that that is faster for you guys than pursuing the eigenvector technique and then finding constants C1 and C2 to fit the data, right? So this is an important method for small systems as well. It's probably faster for initial value problems without qualification. That's probably the case. Any questions? I'll give you guys some homework on this, obviously. I mean, quiz problems on this, and then that should help settle it in. You really need to drill yourself on this until you're bored with it, though, because if you get a half understanding, you'll think you understand it, but you need to be able to do these quickly. And because watching me do it and you doing it in isolation without, phoning it. Whoa. It takes some time to get up to speed on these, all right? And while you do have a page of notes with you, if you actually have to search that page for everything you're doing every time, it's not gonna go well, right? I mean, speed is part of what we're hoping that you get here, some amount of speed, but. And then the other thing to watch out for is just there's a lot of different cases for partial fractions, right? So if there's any section which is worth just killing, it's the inverse transform section. Make sure you know how to do inverse transforms of everything in sight, right? Because that'll sneak up on you. If you accidentally study a subset of problems which doesn't have another kind of calculation in it, it can get you, right? Anyway, just trying to warn you. I have a stupid amount of solutions posted, so you can look at those and ask me questions if you got them. So actually now would be a good time if you have any questions about homework. By the way, I usually will say something like, if I don't want you to do convolution, I will typically include instructions like, if you use convolution, you must actually finish the integral. That's my way of saying don't use convolution here. See, because if you get carried away with convolution, you could always just use it for everything. Like, for example, here would be a misuse of convolution. If I have 1 over s minus 2 times s minus 3, and I want to take the inverse transform of this, I mean, it's not entirely a misuse, I guess, but this would be e to the 2t convoluted with e to the 3t, right? Well, I won't take this as an answer. If you're going to do this, then you actually have to work out the integral from 0 to t, e to the 2t minus v, e to the 3v dv. You know, I actually want you to work that out if you're going to choose this path. What I would prefer for you to do in this kind of problem is to rewrite this, you know, with partial fractions, and so you can get the proper answer. A e to the 2t plus b e to the 3t, whatever a and b happen to be. I'm not going to work them out, but just a warning. Sometimes once you learn how to use a hammer, then everything looks like a nail, you know. The worst case of this I ever saw was when the first time I taught differential equations. I had a couple of really good students, and I taught variation of parameters right before like test 1, and they tried to use it for everything. And variation of parameters is general. It will work for everything, but it's not wise to do variation of parameters on something you can use undetermined coefficients for, because undetermined coefficients calculationally is way easier. Right? So the fact that variation of parameters is general doesn't mean that you should actually use it in general. Right? It's a weapon of last resort. The same with convolution. Anyway. All right, so power series. Let's get started on it. So you need to review all your standard Taylor series, sine, cosine, exponential, cosh, sinh, geometric, all the good stuff. I think what we have time for today, for my example 10. I made it to 10. Feel better. Is to look at something like this. How about y prime prime plus 3y prime plus 2y equal to x. Oh, no, sorry. Let me make this, sorry, I'll get it right eventually here. Plus 2x y equals to 0. Find solution to order x squared. So the basic idea here is to just assume that your solution is a power series. And I guess to be more specific, I'm talking about centered at 0. We're usually doing that. But centered at x equals 0 means that the generic power series looks like this, right? Y equals to a naught plus a1x plus a2x squared plus a3x cubed and a4x to the 4th and so forth, yeah? So we differentiate term by term. And then differentiate again. I kind of expect that that is enough to give me information about the series up the quadratic order. All right. There is a theory of differential equations and power series solutions which tells me that a solution exists. In fact, here, 0 is what's called an ordinary point for this differential equation, which means the solution exists, and in fact is what's called analytic for all reals. Okay, so anyway, we take the derivatives, and then guess what we do? We take these, right? And we plug them in up there. What's that give us? A lot of stuff. So what I'm going to do is just kind of think about it in my head for a second here. And what I'm going to do is I'm going to start with the constant terms. What do I have in terms of constant terms? From y prime prime, what constant term do I have? 2a2. What constant terms do I have from 3y prime? 3a1, right? Are there any constant terms from the third piece, 2xy? No, they're not. That x kills any hope of a constant term being in there. That's it. Them's your constant terms. All right? Next, what is things with x? From y prime prime, I've got 6a3. Right? Maybe I should put the x over here just for the sake of not having to plan how big this is. 6a3. How about from 3y prime? 6a2, right. And then the other one, 2xy. Yeah, 2a0. So I'm collecting all of the terms with x in the differential equation, right? How about x squared? From y prime prime, we've got a 12a4. From y prime, we've got 9a3. From the other one, looks like a 2a1 is in order. And that's enough, I believe. So if this is going to be a solution, and I'm telling you the theory says it will be, all we got to do is figure out how these constants are related. So from the constant terms, I get 2a2 plus 3a1 equal to 0. So therefore, a2 is equal to minus 3/2 a1. From the x terms, what do I get? I get that 6a3 plus 6a2 plus 2 times a sub naught is equal to 0. So I will solve for the highest thing here. a3 is equal to, apparently, minus 6a2 minus 2a0 divided by 6. But you see, by the constant equation above, I can trade my a2 for an a1, right? See if we can clean that up a little bit. That is 3/2 a1 minus 1/3 a0. That's my a3. We didn't even need the x squared. What happens when we get the x squared? (12a4) plus 9a. I'm doing more calculation than I need here, guys. I'm going to change the problem statement to make me feel less dumb in just a second. So I can solve for a4. What did it get me? It get me a4 is equal to minus 9a3 minus 2a1 divided by 12. But that is actually minus 9 times 3/2 a1 minus 1/3 a0 minus 2 times a1 divided by 12, aka a4 is equal to minus 27 over 24 minus 2 over 12. A1 minus plus 3 over 12 plus 1/4 A naught if I haven't made a mistake. We've actually done enough work here to find the solution to order 4, right? We can write the solution to order 4. So I'll say order x to the 4th to make it more interesting. So just to summarize, we found A4 is equal to, what was it down here? I think I've got minus 31 over 24. A sub 1 minus 1 over 4 a sub naught. Do you guys have any disagreements with my arithmetic? I mean, there's a lot going on here. Are we in agreement? All right, so let's put it together. Hence, y is equal to a0 plus a1x plus, what was my a2? My a2 was minus 3/2 a1 x squared. What was my a3? My a3 was 3/2 a1 minus 1/3 a naught x cubed. It was my x to the 4th term was minus 31 over 24 a1 minus 1/4 a naught x to the 4th. Right? Now that is not a good answer. A good answer should indicate the two fundamental solutions as they appear as coefficients of my two parameters in the solution. Second order differential equation should have like a C1 and a C2, right? But in this notation, our C1 and C2 are A naught and A1. And so for A naught, you collect what we have. We've got 1 minus 1/3 x cubed minus 1/4 x to the 4th. Right? And then I have plus a1 times x minus 3/2 x squared plus 3/2 x cubed minus 31 over 24 x to the 4th. And that's the general solution. So this, basically, you could call this thing y1, you could call this thing y2, and you can make the observation that y1, y2 form fundamental solution set. Two star. Could we solve this differential equation before? Why does this differential equation escape our previous methods? No, it is linear. It is linear because like I could write it as the linear operator d squared plus 3d plus 2x acting on y equal to 0. It is linear, but you're on the right path. It just, you're thinking it's nonlinear because it's got x times y. Yeah, that's that's the heart of the issue. But the point is x is non-constant. This is not a constant coefficient differential equation, right? And it's also not Cauchy-Euler. Doesn't have the right pattern. It turns out Cauchy-Euler problems are actually they're the tip of a much larger iceberg, which we deal with something called the Frobenius method. We'll get there. But this is actually not a special example. This is what pretty much we always do to solve series problems. We propose the solution has the form of a series. We plug it into the differential equation, and we work out the math order by order by order, putting together relations between the coefficients. always trying to distill it back to the most basic coefficients. So you try to find the lowest order coefficients that you can write all the higher ones in. There must exist sort of like a lowest non-zero coefficient because, well, it has to do with natural numbers. I mean, you could look at the set of coefficients. There has to be a smallest one, which is non-zero. There has to be a next smallest one that's non-zero. And after you look at the relations that you get from equating order by order, you will be able to write the higher coefficients in terms of the lower coefficients. So this is what's expected of you when you do these problems, is to find the lowest coefficients and write the higher ones in terms of it. When you do that, then you go back, you put it in your initial guess, you'll always be able to pick out two things like this, unless initial data is given. You know, if I told you that y of 0 was 0 here, y of 0 being 0 would force me to put a not equal to 0. Right? Because there's another significance that we have. Y is equal to y of 0 plus y prime of 0 times x plus 1/2 y prime prime of 0 times x squared plus dot, 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 right? Taylor's theorem. So there's a significance to the coefficients as revealed by this Taylor's theorem. In fact, a0 is y of 0, and a1 happens to be y prime of 0. But anyway, enough of that for today. I'll see you guys tomorrow. I hope. Hopefully there'll be 3, 4